Hello there, math fans. I'm going to make a short video here on string and peg art and parabolas because I've had an interaction. Someone actually watched one of my videos. I made this previous video on string and peg art, basically doing I was remembering what I did when I was a kid, which was I connected 1 to 1/5 and then I connected 2/5 to I went a fifth down, and that's how I remember doing this when I was in grade school. Somebody showed me this, and I had never seen what the curve was. And I mentioned in the video that I was a little unhappy with my results. I found what the curve was, but there was this error between them, and I felt like there should be a cleaner way. And I did, but I enjoyed the fact that I got to do some calculus. Well, somebody actually watched my video, and I have a sneaking suspicion that this person is a real mathematician, unlike me. So thank you to, I don't know if that's Chaos, Hangzi. I apologize if I'm mispronouncing, but I appreciate that you engaged with my material in this way. This has been fun for me to explore. I'm just a teacher that has taught. I teach 500 students a quarter. So for me, this has become a break to try to pretend like I could do research. I have just so many ideas, and it's just become a release for me. So I really appreciate you making me feel like a mathematician briefly. So you made they made this comment that, hey, if you connect the point 1/5 to 4/5, it's way easier, and they are absolutely right. And it turns out this is actually a known thing called an envelope. Part of the reason is I couldn't find this. I was searching for like string and peg art, and the envelope, the form is so much cleaner because you get this tangential component. Really, it's defined in terms of the fact that the curves are tangent. In my case, they weren't tangent. So anyways, this is the envelope approach. What I found fascinating is it's the exact same curve that's approached. It's just done in a much prettier way. So this is just, instead of connecting, 1/5 to 1, they connected up here. So nothing connects to 1. So that's different than when I was shown this in grade school. It's different than what I was shown in terms of how to connect. I was told to connect with 1. These ones, nothing ever connects to 1. 1 just gets left dangling off. But what was surprising, it's the same curve. And not only that, it's even better. This case, it doesn't hit those points. It hits here. Mine had this weird extra dangling adjustment I had to make. I think this was a 1/n. I'm not going to... Well, I guess I could pull it up real quick just to compare. Copy. Where did I put that? Here it is. So let's compare. So this one I had a little adjustment. There was a +1 for each one, which made some of the calculations and derivations a little messy, and it wasn't tangent. So if I decrease the number down a little bit, it had this ugly picture. But the cool thing was it still approached, but it bothered me that there was this error. But what I liked about it, and the reason I made the video in the first place, was that error I could then analyze using essentially Taylor series. I didn't go into how that's related to Taylor series, but it was a fun little adventure through errors. So anyways, I really appreciate, thank you so much, someone, for watching. This is the, now what did I do with it? This is the copy I was doing. I can fix it real quick. It's so much cleaner. And I've redone the analysis, and I'll show you that in a moment. Let's shrink this back down so I can see it. Yep, that's it. Again, now that 1 is still dangling. So what I did is I redid my analysis from my perspective. Now, the person who wrote me was nice enough to point to the common derivations people do. I looked at that briefly. I have a new class starting, so I'm trying to not let myself dive too deep into this side thing. I have to watch myself or I'll get sucked in, and I have other things I'm supposed to be doing. But I thought I would just repeat my analysis on this situation and compare. Because I mean, I could go into this, but it seems like we should be able to do the same basic calculus approach to the situation. I think the reason they're doing a more general approach is because they're trying to talk about this property of the fact that each of these is tangent. So anyways, I'll bring this new thing up. Let's add a couple more just so we have something to look at. And what I did was I found these intersections. That's what I did in my solution. So I wasn't considering that tangential. I was probably missing out, but I wasn't considering that as a condition. I was just asking what these points approach, which is different than that other analysis, but it should lead to the same answer. So what's nicer is the second point is this without that adjustment. So this is just the same. If you watch my other video for what I did, I said, all right, what if we connect these 2 points? What's the equation for that line? So step 1, I computed the slope, and I'll make some notes as I go through this. So I computed the slope. It looks kind of messy, but you can simplify it, and it comes out to be pretty nice, relatively. And then I said, this is the equation for a given line. Let's say this first one. This is the equation for the next line. This is what I did in my derivation. And then I found the intersection of those two. Now I saved myself some time here. I didn't write up all the solving and simplifying, but I got a very similar answer. In the previous one, the answer had a different denominator, which made it a little messier. This one's a little cleaner. And then I did exactly what I did last time, which was I said, and this was my weird way of thinking through it. I'm sure other people have done this, but I didn't have anything else at my disposal. So I said, I'm going to assume that the slope of this curve that's going to hit all these points here and here and here is going to get a slope that approaches the slopes of the lines. And it should in the limit. I guess there's an argument to be made there, but we're going to leave that. I said, I believe the slope at a given x value is going to approach the slope of the corresponding lines around it. So maybe that's a harder argument to make here. I don't know. And then I said, and this is the slope of one of those adjacent lines. It turns out you could take the average of these two lines, or you could take the second one, and the limit, it doesn't matter. And then I did this same goofy thing I did before, which I solved this for I. And if you multiply both sides by n, it's a quadratic equation. It can be done. And then I substituted this in for I, and I got to do a limit. This time I won't explain the limit. I'll just go straight to the answer. In the limit as n goes to infinity, this is going to approach 2 over the square root of 4 root x. Watch my previous video about that. And you get this. And I was like, ooh, I was kind of delighted that it gave the same. I did all this before I even looked at it, because I was like, what if I do what he says? He or she, whoever Chaos Jingzi is. I'm probably saying it wrong. But I integrated and I got this. I did immediately ask the question of, well, how do we know C is 1? Because I could see in my solution that it was going to approach 1, because what the intersections were going to approach 1. But how do we know it's 1 and not 1.2 or 5 or 7? How do we know what C is? That was the question I had. Maybe there's an obvious way we should know what that is. So I did some of the same checking I did. I first plugged in the point and looked at the error, and it turns out there still was an error. Because these points are not really touching this. So there still was this error in this case. This time the error is on the other side instead of above. But it doesn't look so much like an error because it's so pretty and it touches the tangent. But there's an error between the point. There's not so much an error between the graphs because the graphs hug it. And I guess that's where the word envelope must be coming from. I don't know. They envelop it. Anyways, I did the same analysis of, okay, the slopes, when are the slopes the same? And I looked for this point because I was kind of mesmerized that they were the same. So I don't know what the next right question to ask is, but I said, okay, assume the slope is equal to the slope of the tangent line. Where would that point be? At first I thought it might be halfway in between, but it's not. So I set this equal to this. I solved and I got x was I squared over n squared. Kind of nice. I plugged it into the original function and got the value, which was this original function. And then I plugged it into the line and I got this value. And I was kind of satisfied that, hey, those are the same, provided we choose a certain value of C. And so there is a certain value of C that will make it so this is always tangent, and that value is 1. Let me zoom out in case in the video you can't see that. So that was kind of interesting. So in finding C, I verified that yes, it should be 1. So that's kind of interesting. This sort of approaches from below. My example approached from above, but approaching from below has this added benefit that the lines are tangent. I sort of wonder, now that I'm just saying this out loud, if my lines were tangent here. Now again, they were much less pretty. And I haven't thought about this till just this very moment, so I should probably stop the video now. But I'm curious if this line was somehow... it would be tangent somewhere. I'm wondering if you took this line and slid it over, if it would be tangent at I squared over n squared. It will be tangent at some point. It's just that's the intermediate value theorem. But where would that be? I think it would be at this, if you intersect, we know that if you intersect this point with that point, it would be tangent. And if we shift this line over, well, anyways, I think I'm going to continue doing kind of, just because what I did was different and weird, I might continue with my different and weird interpretation. But if I do make future videos, I'll mention both situations. And I'm certainly missing some easier perspectives. But really the point of every video I make is just this exploration. I'm no expert on research, but I have many different ideas. And at this point, I'm trying to pass it on to my thousands of students each year. And maybe one of these will be something one of you solve. But thank you for listening and pointing me to some other things. If anybody replies to my videos, there's the likelihood I'll make another video to go with that. So there you go. So now we have a word for this. That's really nice. An envelope. And we have some visuals of that envelope. So we're broadening our understanding of this situation. All right, I'm going to leave.